Hey, yes. Welcome back to the deep dive. Today we're tackling something that's likely part of your daily tech life, or at least something you've heard a lot about. Container technology and Kubernetes, K8s.
Mm.
Whether you're already running apps on it or maybe just trying to keep up in meetings, it's a really key area to understand.
Absolutely. And what's really interesting, I think, is how the tech that makes Kubernetes, easier to use has been quietly getting better.
Right.
Today, we're going to dive into a crucial piece of that puzzle, advancements in container runtimes, with a focus on containers.
Container, okay.
Think of this as understanding a shift, kind of behind the scenes, that makes putting your cloud-native apps to work much more straightforward for you.
Yeah, it wasn't that long ago that getting K8s up and running felt, well, super complicated, especially when it relied so much on Docker.
Oh, definitely. The Docker shim days.
Exactly. But things have become way more efficient, it seems, thanks to these lighter container runtimes like Container.
That's right.
So our goal today is to explain what container runtimes are all about, how they've changed over time, and maybe how they've simplified setting up K8s, especially if you already have some basic understanding of how Kubernetes works.
Sounds like a plan.
Okay, let's get into it. What exactly is a container runtime?
Well, simply put, a container runtime is the software that takes your container image and actually makes it run. It brings it to life.
Just makes it run.
But the term runtime here covers more than just, when your app is active. What's fascinating is that it manages the whole life of the container.
The whole life cycle.
Yeah, the whole thing. This includes giving it the resources it needs, like CPU power, memory, access to storage, the network, all that stuff.
Okay.
And also keeping it separate, isolated from other containers, and the main computer system, the host OS.
The isolation part is key.
Crucial. Ultimately, the runtime is what lets your applications run reliably and efficiently inside those containers.
So it's kind of like the engine and the manager for the container. That makes sense. Now, container technology didn't just appear overnight.
Hmm.
Can you walk us through how these runtimes have gotten to where they are today?
Definitely. I mean, the big moment, as many of you probably know, was when Docker came out in 2013.
Right, Docker changed everything.
It really did. It made container technology popular, built this fantastic system that developers just loved. Docker made it super easy to package and share applications.
hmm
However, as more people use containers and we needed ways to manage, like lots of them together, think Kubernetes Docker's design, which did a lot of things all at once.
Yeah, it was quite broad.
Exactly. It started to show some limits in those bigger orchestrated setups. There was this growing need for something more focused, something more lightweight.
So Docker was great for getting started, maybe on your own machine, but not necessarily the perfect fit for massive Kubernetes clusters.
Precisely. And here's where it gets really interesting. In 2016, Docker made a really big move. They took Containered, the core runtime part, and made it open source.
Ah, okay. So they spun it out.
Kind of. The idea was to take the core piece of Docker that actually runs containers and make it a separate, simpler component. This container was designed to be more focused and, crucially, easier to work with other systems, especially Kubernetes.
Makes sense.
And over time, because Containerd works so well with Kubernetes, it has really become, a de facto standard in the cloud-native world.
Right.
And the benefit for you, the listener, is a more efficient and dependable way to put your cloud apps into action and manage them.
So Container was essentially born from the need for something lighter and better suited, specifically for Kubernetes.
Got it.
Now, I keep hearing about OCI and CRI. These acronyms pop up all the time. What are they and how do they fit into this whole story?
Yeah, they're really important. They represent efforts to standardize things across the container world. Let's start with the OCI, the Open Container Initiative.
OCI, okay.
This was started back in 2015 by Docker and other big players in the industry. Its main goal is basically to create open rules, standards for how container formats and runtimes should work.
Like a rule book.
Exactly. Think of it as setting the common language for containers. So everyone agrees on how they should be built and how they should be run.
So does that mean different tools can work together better?
Precisely. The OCI has two main sets of rules or specifications. There's the image specification, which says how container images should be packaged up.
Okay.
And then there's the runtime specification, which says how containers should actually be run.
Image and runtime specs. Got it.
What's really cool about this is that these rules mean different container runtimes like Docker, Containered, even another one called CRIO, can all run the same container images.
So I'm not locked in.
Exactly. This gives you a lot of choice. You're not stuck with just one runtime vendor. You can pick the one that works best for you.
That sounds really helpful. Okay, what about CRI then?
So CRI stands for Container Runtime Interface. Its job is different. It provides a standard way for Kubernetes itself to talk to different container runtimes.
So it's the K8s to runtime communication standard.
You got it. Think of it like a universal adapter plug. It lets Kubernetes communicate with various runtimes without needing to know the specific nitty-gritty details of each one.
Makes sense.
Both container and CRIO are designed to use the CRI standard, which makes them work really smoothly with Kubernetes.
Okay, so OCI is about the containers themselves, the image format, how they run, and CRI is about how Kubernetes talks to the things that run them, the runtimes. How did Docker fit into this when CRI came along? Because you said container uses CRI.
Right. This is a key point in the history here. Docker didn't directly implement the CRI standard itself. Instead, Kubernetes needed a kind of go-between piece. It was called Docker Shim.
Docker Shim, I remember that.
Yeah, it acted as a translator between Docker's own way of doing things and the CRI that Kubernetes expected. But this added extra complexity. It was another moving part.
Another thing to manage or break.
Pretty much. And as Containered and CRIO got better at directly using CRI, the need for Docker Shim kind of faded away. In fact, Kubernetes completely removed Docker Shim, starting with version 1.22.
Wow, okay. That's a big change.
It was huge. And it's a major reason why you now see Containered and CRIO being the recommended runtimes for Kubernetes. It just simplified that whole connection.
So getting rid of Docker Shim really cemented CRI native runtimes like Containered as the way to go for K8s. Now, zooming out a bit, how has all this evolution in container runtimes actually affected cloud-native setups? What are the real benefits for, someone listening to this?
Oh, the overall impact has been massive. We've seen significant improvements in how applications are deployed, how they're managed, how they're secured, and the flexibility we have now.
Okay.
This all leads to businesses being able to deliver services faster, more efficiently. But let's break down some of the main advantages for the user.
Sounds good. Well,
First, lightweighting and performance improvement. As we've touched on, runtimes like Containered and CRIO are much smaller, more focused than the full Docker engine used to be in that context.
right, less baggage.
Exactly. This means containers can often start up more quickly, and they generally use fewer system resources, less CPU, less memory.
And for me, that means?
For you, this means faster deployments, potentially packing more containers onto your servers, and maybe even lower infrastructure costs.
Faster and cheaper. I like the sound of that. What else?
Second big one is standardization and interoperability, the ability to work with different systems. OCI and CRI has been absolutely key here.
The standards again?
Yep. CRI especially allows Kubernetes to easily plug and play with different compatible runtimes. This gives you more options, right? And it prevents you from being locked into a single vendor's ecosystem. You can choose the container runtime that best fits your specific needs for your Kubernetes setup.
More choices are definitely good. How about security? Is there an impact there?
Absolutely. Lighter runtimes can also contribute to better security.
How so?
Well, by having less code and fewer dependencies, there's just a smaller attack surface, fewer potential weaknesses that could be exploited. Container, for example, focuses just on running containers, which can lead to better isolation between them and makes it easier to integrate with Kubernetes native security policies, like pod security policies or admission controllers.
So less code, fewer features means fewer places for bugs or vulnerabilities to hide.
That's the general idea, yes. And finally, there's the flexibility of cloud-native architecture itself. Having different runtimes available allows you to pick the best tool for different jobs. This fits really well with modern development paradigms like microservices.
Right.
Maybe one runtime is slightly better for certain types of workloads than another. This gives you more fine-tuned control over your infrastructure.
Okay, it really sounds like these changes, the lighter runtime standardization, have brought a lot of tangible advantages. Now, you mentioned containers becoming more common than Docker, specifically in Kubernetes environments. Can you walk us through why that shift happened? What were the key moments?
Certainly. As we discussed, Docker was incredibly important after 2013. It popularized containers, became the go-to tool for developers, for companies dipping their toes in.
Yeah, it was synonymous with containers for a while.
It really was. However, over time, that monolithic nature, doing many things, became a bit of a limitation, especially with Kubernetes rising as the dominant container orchestrator. This wasn't really Docker's fault, per se, but more of a natural evolution as the industry's focus shifted.
Shifted from what to what?
Well, it sort of shifted from just how do I build and run a container on my laptop to how do I efficiently manage and operate potentially thousands of these containers across a whole cluster, more of an operations focus.
From dev to ops, in a way.
Exactly. The key moments really illustrate this.
Mhm.
2016, Docker makes that strategic decision, separates containered, makes it open source. The goal was simplifying that core runtime logic, making it modular. Initially, it was still tightly coupled, but it set the stage.
Okay, step one.
Then, 2017, this was big. Container joined the CNCF, the Cloud Native Computing Foundation.
Ah, the home of Kubernetes.
Precisely. This gave it huge community backing, visibility, and governance. And critically, around this time, Containered added proper support for CRI, making it a first-class citizen for Kubernetes, essential for large-scale K8s workloads.
So CNCF boosted its credibility, and CRI support made it technically ideal for K8s. What happened next?
Well, by around 2019, you started to see Docker Inc. repositioning itself, focusing more on developer tooling, Docker Desktop, Docker Hub. Kubernetes had pretty much won the orchestration war, right?
Yeah, that seemed clear by then.
So Docker's strategy adapted. Meanwhile, Container was steadily becoming the preferred runtime in enterprise Kubernetes environments because it was lightweight, stable, and integrated so well via CRI.
The momentum was building.
Definitely. Then came 2021, Kubernetes version 1.22. This was the version that officially deprecated and later removed Docker shim support.
The final push.
It was a very explicit signal. The K8s project essentially said, use a CRI-compliant runtime directly, clearly recommending options like Containered and CRIO.
Okay, that must have really accelerated adoption.
Absolutely. And if we look at where things are now, roughly 2025, Containered is widely used. Major cloud providers, AWS EKS, Google GKE, Azure AKS, they all use Containered under the hood by default now.
Wow, all the big ones.
Yep. And it's common in on-premise setups, too. It's lightweight, it's standards compliant, it integrates seamlessly with Kubernetes. Now, it's crucial to note, Docker is still incredibly useful, especially for local development, building images, testing things out on your machine. Docker Desktop is great.
Right, it hasn't disappeared.
Not at all. But for running Kubernetes in production, particularly at scale, Containered has largely become the standard choice.
That timeline really makes the shift clear. Okay, let's get practical. You mentioned setting up Kubernetes has become easier with Containered.
Yeah.
Give us a simple comparison. Setting up K8s with Containered now versus how it maybe used to feel with Docker. Focus on why it's easier or perhaps just different now.
Sure. Let's look at some key areas side by side, focusing on the K8's context. First, the container runtime itself. With the old Docker approach, you installed the full Docker engine. Now you install just Containered, a more focused component.
Okay, simpler component.
Regarding OCI compatibility, Docker did support OCI standards eventually, but it also had its own history and formats. Containered was designed from the ground up, essentially, around OCI, aiming for full compliance. This generally means better interoperability for you with other OCI-compliant tools.
So Containered is more purely OCI focused.
You could say that. Now, CRI compatibility, this is a huge difference, as we discussed. Docker needed Docker shim. That's gone now. Containered implements CRI directly. Meaning a cleaner, simpler, more direct integration with Kubernetes, fewer layers, fewer potential points of failure for you.
Simpler connection sounds like fewer headaches. What about the actual setup process itself? Is Containered harder to install or configure?
That's a nuanced one. Initially, maybe using Container's lower-level command line tools like CTR or nerdshittle, if you use that, might have felt a bit more complex than the very familiar Docker CLI that everyone knew.
Right. Docker Run is pretty intuitive.
It is. However, the overall process of installing Kubernetes with Containered has become much smoother. The tooling like Kubedem handles the integration well, the documentation is clear, and the fact that Kubernetes expects a CRI runtime like Containered makes the whole thing more streamlined now.
So maybe the individual tool commands felt different at first, but the end-to-end K8 setup is actually smoother because they're designed to work together now.
Precisely. And Kubernetes compatibility itself, Docker engine support via Docker shim, is gone in modern K8's versions. Containered has native, stable, ongoing support that's critical for your cluster stability and future upgrades.
Can't argue with that. What about resource usage?
Generally, because Containered is more lightweight, focused only on the runtime aspects and not all the other things Docker engine did, it tends to consume fewer resources, CPU and memory. This can be significant in large clusters, potentially improving overall performance for you.
Lighter's usually better in production.
Usually, yeah. And just quickly on use cases, Docker, as we said, still fantastic for local development, build pipelines. Container really shines for stable, efficient runtime management in Kubernetes clusters, especially in production or scaled environments. That's where it's become the preferred choice.
Okay, that's a really clear comparison. It sounds like the move to container within the Kubernetes ecosystem is fundamentally about efficiency, standardization, and better integration with K8s itself. So to hammer this home, what are the main advantages, again, of using containers specifically with Kubernetes?
Okay, let's list them out. First, it's lightweight architecture. Lower resource consumption, efficient, especially good for large clusters. That's a benefit for your capacity and costs.
Uh,
Second, OCI and CRI compliance. This means interoperability with the ecosystem and, crucially, seamless native integration with Kubernetes. Simpler setup and management for you.
Native integration is key.
Third, building on that, is the tight Kubernetes integration. Because it speaks CRI directly, it ensures stable operation with the latest K8s versions, no intermediaries needed.
Okay.
Fourth, its design is modular and extensible. This can make it easier to customize or maintain if needed, though most users just use it as is.
Good to know.
Fifth, open source community support via the CNCF. Active development, updates, security patches, reliability. That gives you peace of mind.
The power of open source.
Exactly. And finally, security. That reduced attack surface we mentioned, focusing on core runtime tasks, plus better integration with Kubernetes security mechanisms.
So it's lighter, standards-based, integrates tightly, modular, community-backed, and potentially more secure in the K8s context. That's a pretty compelling list. Now, for someone listening who, say, understands K8s basics and might be thinking about setting up a cluster themselves, perhaps for learning or a small project,
Yeah.
can you give us a simplified overview of how a container-based installation might look, just highlighting the key steps and maybe why they matter?
Absolutely. Let's do a high-level walkthrough, focusing on the why. First, often you need to deactivate swap memory on your Linux machines. Kubernetes generally requires swap to be off for performance and scheduling reasons.
Okay, disable swap. Got it.
Then you'll typically need to set up some kernel modules and system control parameters, things related to networking like burnet filter. This is basically enabling the underlying Linux features Kubernetes networking relies on.
Preparing the OS for K8s networking. Makes sense.
Next comes installing and configuring Containered itself. You install a package, then you edit its main config file, usually at etc/containered-config.thomasbarrel. A really important setting there is making sure it's configured to use systemed as the C group driver, because Kubernetes typically expects that now for resource management.
Aligning containers resource management with K8s.
Exactly. Then you start and enable the container service so it runs automatically. That's your core container runner in place.
Okay, system ready, container installed, and running with the right settings. What's next?
After that, you install the main Kubernetes components, kubelet, which is the agent that runs on every node and talks to the container runtime, kudium, which is the tool we'll use to bootstrap the cluster,
Okay.
and kubectl, the command line tool you use to interact with the cluster once it's running.
The essential K's trio.
Yep. Once those are installed on your control plane node, you initialize the cluster using kubidium in a NIC. And a key part of this command, connecting back to our discussion, is telling kubidium how to talk to container-died. You do this with the CRI socket flag.
The direct connection.
Exactly. You point it directly to container ordered's communication endpoint, usually something like unix.runcontainer container.sock. No Docker shim involved.
Much cleaner.
It is. After kubium init finishes successfully, it gives you instructions on how to set up your kube config file. This file holds the credentials and information Kubectl needs to connect to your new cluster.
So you can actually control it.
Right. You might also want to install helper tools like K9s for easier cluster management, but that's optional.
Okay, cluster's up, I can talk to it. Now what?
Now you need networking between your pods, your containers. You have to install a network plugin, also called a CNI plugin. Calico is a popular example, but there are others like Flannel or Cilium. This allows your applications running in different pods to communicate.
Crucial for apps to work.
Absolutely. Then, if you have other machines you want to act as worker nodes, where your apps will actually run, you join them to the cluster using the kubein join command that kubein init gave you earlier.
Scaling out the cluster.
Yep. Finally, you verify everything's working, you run kubectl and ax, get nodes to see if your control plane and worker nodes are all showing as ready.
The moment of truth.
Pretty much. You can also optionally allow workloads to run on the control plane node, though that's often not done in production. And importantly, if something goes wrong, kubeatum reset is your friend to clean up and try again.
Good to have an undo button.
Definitely. So following those general steps gets you a Kubernetes cluster running with containered, benefiting from that tighter integration and efficiency we've been talking about.
That sounds much more straightforward than maybe the perception was a few years ago. Now, you've mentioned OCI and CRI quite a bit as key enablers. Can you try to explain their role again in standardizing things, maybe using a really simple analogy?
Okay, let's try that music analogy again, maybe slightly differently. Think of OCI as the standard for musical instruments themselves. The OCI image spec is like the standard design for a guitar. It defines the shape, the number of strings, how it's tuned, so any guitar built to the standard can be played. The OCI runtime spec is like the standard physics of how sound waves work when you pluck a string, how the instrument actually produces sound. Runc is like a perfect guitar amplifier that implements these physics.
So OCI defines the instrument, container image, and how it makes sound runtime execution.
Exactly. Images built to the OCI spec, standard guitars, can be played by runtimes that understand the OCI runtime spec, standard amplifiers like Runc, used by containered, CRIO, etc.
Got it. What about CRI then?
CRI is like the conductor of the orchestra. Kubernetes is the conductor. CRI is the standard set of hand signals and instructions the conductor uses to tell the musicians, the container runtimes like container, what piece to play, when to start, when to stop, how loud, etc., using their standard instruments. OCI container.
So Kubernetes uses CRI signals to tell container what to do with the OCI standard containers.
Precisely. Because Kubernetes uses the standard CRI signals, it doesn't need to know the specific internal workings of containered versus, say, CRIO. It just knows they both understand the same conducting signals. This allows Kubernetes to manage different runtimes easily.
That music analogy really clicks. So OCI standardizes the what, the container image and its execution, and CRI standardizes how Kubernetes manages the things that run the what.
Yeah.
Can you briefly recap how each achieves this standardization technically?
Sure. OCI, as we said, has specifications. The image spec defines the layout image layers, manifest list of layers, config file. This ensures portability. Build an image with Docker, run it with containered. The runtime spec defines the container state, configuration, and lifecycle operations for tools like Runc, which containered uses under the hood. It ensures consistent execution.
Okay, OCI specs define the package and execution rules. How does CRI do its part?
CRI defines an API, a contract between Kubernetes, specifically the kubelet component on each node, and the container runtime. It has two main parts. The Runtime Service API handles pod and container lifecycle management, create, start, stop, remove pods and containers. The Image Service API handles image management, pull images, list images, remove images.
So standard commands for pods and images.
Exactly. Any runtime that implements these gRPC API services like containered or CRIO can be used by Kubernetes. And as we mentioned, the CRI shim was that temporary adapter for runtimes like older Docker that didn't speak CRI natively.
Right, the translator that's now gone.
Yeah.
So how do OCI and CRI work together in practice?
They work in layers, complementing each other beautifully. Kubernetes kubelet talks to the runtime, like container, using the CRI API calls. Please create this pod. Please pull this image.
Okay.
The CRI-compliant runtime container receives these instructions. To actually execute them, like running the container, it then uses OCI-compliant tools like Runc and follows the OCI runtime specification. To handle the image, it uses the OCI image specification format.
So K8 uses CRI to give orders, and the runtime uses OCI standards to carry them out.
You've got it. This layered approach provides end-to-end compatibility and allows for optimization. Lightweight runtimes like containered can integrate directly with Kubernetes via CRI, reducing overhead, and then rely on the well-defined OCI standards for the actual low-level container operations. It's efficient.
That really clarifies how these two sets of standards fit together to make the modern Kubernetes ecosystem work so well. Okay, to wrap things up then, can you give us a quick summary of the main journey we've taken today?
Absolutely. We've really traced a significant evolution, haven't we? From the early days where setting up Kubernetes often involved the full Docker engine and the complexities of Docker shim, to today's much simpler, more efficient deployments using streamlined CRI native runtimes like containered. This whole shift has been fundamentally driven by the industry embracing open standards, OCI for container formats and execution, and CRI for the Kubernetes runtime interface.
And what does this whole evolution mean for our listener, for you, working with this tech?
Well, for you, this translates directly into several key benefits. It generally means an easier, more straightforward Kubernetes installation and setup process. It means potentially better performance and more efficient resource utilization in your clusters.
Good stuff.
It contributes to improved security thanks to those more focused, lightweight runtimes having a smaller attack surface. And ultimately, it gives you greater flexibility and choice in building and managing your cloud-native applications, ensuring better interoperability within the wider ecosystem. The move towards containered as a standard runtime for Kubernetes really provides a more robust, streamlined, and reliable foundation for deploying and managing your apps.
That's a fantastic summary.
Yeah.
It really is amazing how much progress has happened, often quietly behind the scenes, to make working with powerful tools like Kubernetes, well, less painful and more effective.
Yeah.
On that note, here's a final thought for you, our listener, to maybe ponder. Given how much container runtimes have already improved, driven by these standards and community efforts, how do you think these advancements will continue to shape the future of cloud-native systems? What new possibilities might these simpler, more efficient, and standardized foundations unlock for your own projects, your learning, or maybe even entirely new architectures we haven't thought of yet?
Mm, that's a good question to think about.
We definitely encourage you to keep exploring the fascinating and still evolving world of Kubernetes and container runtime technologies. Thanks so much for joining us on this deep dive.